And welcome back. Now let's actually get real and explain to you how to actually work with real memory. So this is what makes C different from Java and Python. You're going to have control of how much memory you get and how much you want and how to release it and do all those things. Let's talk about it today. So we learned that C has this size of function, which gives the size in bytes of the thing you pass in. That's great. And that can be a type or it can be a variable, which is nice. And back in the day, ints were 16 bits, so you could ask size of int 30 years ago, 40 years ago, 30 maybe, and it would say 2. And now it'll say 4. Maybe now it'll say 8 soon. Size, this is again why I use int types, if I keep saying that. So size of knows the type of array. If I have int AR of 3, size of AR says 12. That's 3 integers, and so 3 times 4 is 12. As well as integers that you know at runtime. So, here is AR of n, which is a dynamic number, or it's a function that returns 3, and you say int AR of some function which evaluates to 3, and AR of that, which is 3. Do it again, it'll still say 12 for the size of the number of bytes you've got. So, this is the first time we've ever talked about this in this class. The way you ask for memory dynamically, aside from the array, there's an array, we talked about that before, is using malloc. And we'll talk about what the difference between malloc and an array is soon. So here's the first time you've done this. So I say pointer. I've got a pointer to an array of integers. I'll say array of integers. I declare it malloc. So malloc is a function that takes in the number of bytes you want and returns a pointer to uninitialized space. So it's not initialized. Remember, C never initializes these for you. And it also returns it as a void star, because it doesn't know what it wants in general. It's going to return a void star. Remember, void star is a pointer to generic space, to the generic array. You have to cast that. So you have to say, if pointer is declared an int star, so int star pointer, you have to then cast that with this, and that tells the system, don't worry about it. I know malloc returns a void star, but I want to cast it as an int star so that the equal sign matches up. The right side of the equal is an int star, the left side equal is an int star. So that's good, okay? That's all it is. It's called a typecast. We've kind of seen that. That's the first time you've seen that, actually. Malloc, however, is almost never reserved. Why would you malloc just to get one integer? If you just want an integer, make it an int. Make it, foo. Int foo, there's an integer. You probably want an array. You probably want a lot of them. So this is the way it typically is done. Pointer equals int star malloc, and you have n times size of that. So that says I want an array of n integers, and pointer points to that array. Now it's not a static array with the square brackets, but it is an array nevertheless. We still call them arrays. So once malloc is called, the memory location contains garbage. You know this, right? You know that we never initialize things. We never reset things. C is too fast. So that's going to be an uninitialized set of, if it's 3 integers, it's 3 garbage integers, just 12 bytes of nothing. Who knows what they are? The key is, when you're done with that space, whatever that malloc returned, that's a value. That's a pointer to the beginning of that space. You eventually need to free it. And there's a kind of a contract. There's a contract between malloc and you. It's almost like, I don't know, it's almost like going to the Godfather and asking for a favor. Godfather, I would like some memory from you. Someday, and the day may never come, I may call upon you to do a favor for me. But until that day, I will give you some malloc under the contract that you must free it when you are done. That's my Godfather imitation. So, even though the program's going to free it when you're done, don't do that. Don't let the program free it for you. Make sure you free it yourself. Why? Because you never know when your main becomes a subroutine. You say, oh, this is a pretty cool thing. Let me wrap it in a subroutine. And over here, by the way, but you never freed it. So now this main never frees it. We call this a memory leak. And all of a sudden, that's a subroutine now. Now you're going to call it many times, and all of a sudden, all that memory you asked for, it just gets spilled. It doesn't get spilled. It gets leaked. It gets leaked. It's a leak of memory, and that's really bad. So you don't want that. So definitely listen to the Godfather and free it at the end when you're all done. And there's a lot of details to this. You can't use it after you're free it. Once you're free it, you're all done. So whatever malloc gives you, that pointer, you better pass that same pointer to free someday. Use it, then pass it to free, and then you can't use it after that. Again, important thing. So here are some things that are going to bite you. We're going to see this a lot because I want to make sure you see all these things that'll bite you because they will bite you. They bit me. They basically bite every beginning programmer. The following two things will cause an error: freeing the same piece of memory twice. I told you that. Once you free it once, you can't touch it again. It's out there and it can be reused maybe, so you can't free it twice. You also can't call free on something you didn't get back from malloc. So here's a malloc. You can only call free on that guy. You can't free it for anything else. If you move the pointer, you can't call free on the new pointer. You have to call free on the exact address passed back from malloc. Okay? So it's kind of three things you can do wrong. If I told you malloc and then free that guy eventually after you're done with it, well, you were done with it, but then you freed it twice, bad. Or you called free and then on something that was not that, or you didn't free it at all. A lot of ways you can mess up. And the runtime doesn't check for it. It doesn't check for this. Memory, C is too fast. C is too performance critical. Doesn't do this. Your code's going to be either left in an inconsistent state because you've messed with the memory allocator somehow, and you won't find that bug until way later, which is bad. You're running a server and all of a sudden, hey, why does the server crash? Yeah, because you did some weird thing with malloc and free back then, and then eventually you paid for it later. Really bad. Kind of like not brushing your teeth. Brush your teeth because years later you'll pay for it, trust me. I'm fine, but the point is that. Now, you can, turns out, okay, you malloc something, big space. Okay, but, interesting. What if I wanted to make it bigger or smaller? Could I actually resize it? And says, sure. So it's called Realec. Realec takes the pointer, the original pointer that malloc gave you. So, you know, I get a return of guy from malloc as a pointer to that. I could say, you know what, I want it more now. I want twice as much, or 5 times, you know, 5 times as much, or I want it smaller. I can call Realec, and that returns a new pointer. Now, what I didn't tell you, this is the thing on the previous slide, malloc sometimes can't satisfy your request. I'd like 4 trillion billion, I'd like 1 billion integers. I'd want some amount of space. And maybe the space is run up. Maybe all the space you had access to is full. Malloc has to have a failure mode. Let's think about it. What's its failure mode? Before I told you at the Unix level, when you return a 0, it's success, everything else is a failure. But here, what is the sentinel for memory? What's the single value that malloc could return that we know could never be a valid value that malloc could return? 0, null. So every call to malloc had better have the next line you check to see if the pointer equal null. Now, one of the early mistakes people make is check if pointer equals null. Well, pointer equals null assigns pointer to null, and now all of a sudden you've leaked the memory that malloc gave you. Malloc gave you some memory, then you just erased it, so now you have no way to get back and free it again. That was bad, because you overrode it by saying pointer equals null, and it's always going to be false, even though malloc actually was successful. So that's a buggy thing. So pointer equal null. So it turns out what people do is they'll write null equal pointer. But if you ever mistake it with one equal sign, null equal pointer doesn't make any sense, and that'll be an error there. But null equal pointer actually works. So they'll flip it around. Really interesting. So you test if null equal pointer as a way to make sure that it's there. And if, null equal pointer. And if that's the case, then you say, error, I couldn't get memory. You gracefully handle it, and you do something else. Say, hey, sorry, you asked for a big, some memory. I couldn't give it to you. Otherwise, you keep going, and you got the memory. You can now use it. So the line over here on the right says, IP integer pointer equals this malloc guy. I've asked for 10 integers, and you always check for it equal to null after that call. Then I'm going to reallocate it. Say, you know what? I want to make, I said 10, I said 20, I really meant 20. I meant 20, and so you reallocate all of a sudden to 10, now it's 20, okay? Now the key is, it is supposed to, if it's bigger, it is supposed to move the material over. If it might actually give you, say, I don't have 10 here, but I have 20 over here. I have 20 here, but I have 20 over here. So actually, I'll go here, and what it's supposed to do, if it all works, it's supposed to move the 10 over, whatever content you had in there, you filled it with 10 values, 1 through 10. I moved over here, and now I've got 20 I can access. It's supposed to have moved the original 10 over. So it's actually pretty cool to do it automatically. So Realec is really nice, but check it. It might not have worked. So make sure you check it, make sure that the content is, first of all, check if it's null, and also check if it did the resize correctly. If it doesn't work, it's 0. It'll return null, and it's there. If you want to free it, I don't recommend this. I would prefer you call free. You can say Realec IP0. It's the same as a free. It says, you know what? I don't want anything anymore. That's the same way as calling free. But I prefer to call free myself explicitly. Now, arrays are strange. Arrays are not implemented as you'd think. Let me get my pen here and make sure I've got this going. So here's a piece of code, foo. And here's an array. First line. Okay, here we go. Int Star P, star Q, and X. X is an integer. What's its contents? Garbage. P and Q are pointers. What's their contents? Garbage. When pointers have garbage contents, we draw their pointers as kind of pointing who knows where. This is like who knows where, I don't know. Here is int A of 4. Now, where does A live? I don't know. See, arrays are not implemented like you think they would be, okay? But A of 4 says, here's 4 integers. I'm going to give you, and they're all contiguous. We know they're always contiguous. Malloc returns you contiguous memory, and so does A of 4, okay? So now, here we go. Let me clear this here. Next line. P equals, there's like the 3 ways to do this now. Well, I mean, there's the raw way to say int x. Here's A of 4, that's an array way, and now there's the malloc way. That's why I'm showing you this one. This says P equals int star malloc size of int. Just makes one int. Again, usually don't call it, usually say n times size int or some size like that. So I make a new integer. So what happens? Over here is the result of malloc. Okay, that's the result of malloc. I made some new space. I made an integer, and P is going to point to it. When something points to something, its address, here 40, is the value of the pointer. So at 40, 40. Makes sense, okay? So P points to that malloc integer over there. Now, Q equals address of X. So now Q is going to point to X. X doesn't have a value yet, but it points to it, okay? So I've got these 3 uninitialized integers, 1, 2, and 3. Let's see what actually is going to happen. Here we go. Star P equals 1. Okay? I follow the pointer, and I stuff a 1 there. That's as a result of that line, star P equals 1. Okay? And so now, if I ask for P, star P, P, and address of P, what should it give me? Star P, follow it, okay? P, there's P. What's address of P? Okay, so let's see what it prints out. Ready? Boop, star P1. P is 40, address of P 12. Makes sense, right? Thumbs up. Now, next line, star Q equals 2. Remember, this guy was uninitialized still. Star Q equals 2. There we go. And now let's ask for star Q, Q, and address of Q. Okay, here we go. Ready? Star Q, 2, Q, 20, address of Q, 16. 2, 20, and 16. Any questions? Pretty good, right? I'll wait. Feel free to ask your question. I'm too used to doing this dynamically. This video thing is very strange, by the way. I just need to say, doing this in front of a camera is very strange. Finally, star A is 3. Let's see what happens. Ready? Bloop. Okay, so what A was pointing to is now 3. Here we go. Star A, address of A. Let's do it. Ready? Here we go. Star A, we know it's 3. A, well, we got to have 24 because obviously that's what it was. That's what is there. Where does A live? What's the address of A? Let's just see this. It's a little strange. Ready? Hear that glass breaking sound? How is the address of A 24? How does that make any sense? That's not what, address of A isn't 24. This is an A. That's not, doesn't make any, so A is 24, right? A, the value A, that points to 24. So this guy has 24 inside of it. But the address, where does A live? That's not 24. The reason is arrays are not implemented as you think, or as KNR says, an array name is not a variable. You're going to see when we get to the assembly level why that is. Remember this, hold this weird, uncomfortable feeling right now, because when we get to assembly, you're going to see, oh, now I know. Remember that slide Dan showed me? Now I know why that is. So, mini summary for this little mini lecture here. Pointers and arrays are virtually the same, except for that little exception I showed you about there, about where they live, and that you can't increment an array, open square bracket variable. C knows how to increment pointers, plus and minus. It knows what the size of it is and moves them around. It's an efficient language with little protection. It's basically going to let you hurt yourself. It's a very sharp-edged car. A very sharp-edged car with no plastic around you, just a wild engine running there. Use handles to change pointers. I said that. We saw The Godfather, where you can use Malloc and free, but you got to promise to return and free the stuff you borrow from the memory you borrow using Malloc. And you get something, you know, ain't no free lunch, folks. Ain't no free lunch. What do you get for that speed? What you get for that speed is a lot of rope. That speed is remarkable, but you get a lot of rope and you can hang yourself with it. So don't. Know about all these gotchas and try to avoid them. See you at the next lecture.